calling Slumdog Millionaire, and James Gresh, calling King James the Gross. Look it up. And we're setting up to test, in the crudest possible fashion, our 3 brand new Panasonic HIT panels. These are 96 cell panels that are black on black over black. We like black here at EVTV, as we've always said. Paint it black and it'll disappear. A month ago, I tried to order some ENphase IQ7x microinverters and failed at a number of places. One actually sold them to me, and then 2 weeks later had to inform me they just had actually gotten any in. And in spite of it, the fact it's saying in stock now, they weren't in stock now. 2 weeks ago, I tried again. These were supposed to be available in May. The 2 weeks ago order, I got them last week. We got 5 of them. James, show them your thing. The interesting thing about that is they've had microinverters from Hoy Millies in China and ENphase here in the U.S. for some time. They've typically been limited to 60 or 72 cell units. This is a 96 cell panel, 325 watts. What's the open circuit voltage of the panel?
70.5.
70.5. And what's our range of DC input on the ENphase IQ7x?
25 to 79.5.
There you go. And that's the magic. These have been developed by ENphase in cooperation with Panasonic, specifically as ostensibly the first 96 cell microinverter. These are good for what, about 300 watts or 350, and these panels are about 325. We have got them hooked up. Dan was kind of showing you. They hook right up to the cables off the panel. You have to buy a special and kind of expensive cable to hook up to the ENphase for the AC. And we've got that wired to a very deluxe outdoor extension cord of 100 feet to run it all the way into our PowerPhase100 and see how that goes. Danu, how long did it take you to hook that up?
Less than 5 minutes.
Less than 5 minutes. And so we've invested some time and effort in this test setup. And so that's the point. Actually, I haven't. Jim and Danu set this up for me and wired it up to the PowerPhase100. And we're going to go see if these work the same as our Solar Edge grid-tied inverters. These have to have a 240 volt. Now, this cable is 2 wires. What, red and black, right? Yep. And that's a 240 volt output, no neutral. And we are going to wire that into our inverter and through the charge enable contactor so we can turn it on and off and see how it works with our Engineer inverter to determine if it will charge the batteries in AC coupled fashion, in the identical fashion as the Solar Edge, or a similar fashion, I would accept, and see if we get some power out of these panels. Now it's 4:30 in the afternoon. I actually asked them to tilt them. I meant that way. They tilted them this way because the sun is far to the west. So to get a little more power, but they're hardly optimum. They've still got the crate stackers on them that we're using, and this is just to test the concept. Will the ENphase IQ7x, now available at the higher voltage, they'll do 79 volts. These panels have a maximum open circuit voltage is 70.5 volts. So a good fit there, and they should very efficiently take each panel. I'm shadowing this one, but that won't diminish the output of an Mppt maximum power point tracking on the two that are getting full sun, and they all contribute their AC to our trunk line into the PowerPhase 100 solar input through our charge enable contactor. We should be able to manipulate that contactor and actually turn this off and on. Let's go inside and take a look.
Let's do a quick review for those of us, for those of our viewers who have not been watching EVTV over a number of months. We are proposing a couple of oddities in solar that are somewhat unusual. We call this selfish solar, and the overall basis of it is that we're using the grid as backup only instead of using batteries as backup. We want to make our power with solar panels, and we want to store it in batteries, and we want to use that to generate 240 volts AC to operate our buildings. We're not concerned with putting power back into the grid and storing it there. We don't care if they pay us anything for it. Our whole concept is to pay the $11.24 a month to have a grid connection and not use any of it. But we'll use it as we have to, depending on time of year and weather variations. But we're going to try to size our system to where our batteries and our solar panels basically cause our state of charge to go up and down within kind of an 80 to 20% band on a daily basis. And we're going to make our own power, and we're going to use our own power. In other words, generate power at the point of use, and that's why we call it selfish solar. We're not going to share our power with other people, and we don't want to use, and we want to minimize the use of power from outside of here. For off-grid applications, this could be replaced with a generator. And in fact, we have a generator start signal out of our 12 kilowatt inverter, which we have had designed specifically for Tesla voltages by a company in China called Sinjinier. Aside from it being selfish solar, the other very unusual component you just won't see because people don't know you can do this, and we've kind of been proving that you can, is we're AC coupling the solar into our inverter and our batteries, which anyone in solar will tell you can't be done, and we've been doing it routinely now for about 8 months. So here is our Tesla battery module, in this case our PowerPhase 100, and we have actually 20 modules for 100 kilowatt hours of storage, but we are at 48 volts DC, and we feed that into a 12 kilowatt inverter that runs on 48 volts. It can put out 12 kilowatts. It can peak out at 36 kilowatts, but it's nominally a 12 kilowatt inverter, and we would normally want to stay below that. You can see in the inverter that there is a transfer switch. Now in AC priority mode, we can take AC and we can both pass it through to our loads panel and use it to charge our batteries. And that's a very interesting feature of this inverter. In battery priority mode, this would normally be disconnected, and we are doing all our power from batteries, and we would not switch to AC until we get to a low voltage cutoff, which we're measuring about 38.65 volts as being a low voltage cutoff, where this will switch over, and we can start charging our batteries from the grid or the generator, and we have a generator start signal to start that. We don't really ever want to do that. We want to operate in a band where, in battery priority mode, where we're using the batteries. And our output goes to the loads panel. And we have done away with combiner boxes, Mppt charge controllers, auxiliary chargers for our batteries, and we're trying to use a much simplified system of grid-tied inverters. We have some wall-mounted solar edge inverters in the shop, but today we're testing the ENphase IQ7, and they would be on the roof, one per panel actually, and then they would have a 240 volt AC trunk that would go to a junction box on the roof, and then a simple house wiring cable down to our loads panel, usually through a circuit breaker, into the loads panel. We want to go through a contactor which is energized by our charge enable signal from the PowerPhase100 battery module controller. And so we can turn on and off this array. Now, why would we want to turn it off? Well, if our battery gets full, we want to stop charging. We have to have some place for the excess power generated by this to do. So this is an AC coupled system, a DC coupled system. We would normally have the panels and then Mppt charge control, and they would connect here at the battery before the inverter. In this case, in our AC coupled system, we connect where this is. Now, what are the advantages? Well, as I said, you eliminate a lot of equipment. We don't need a special charger for a battery. We don't need an Mppt charge controller. We don't need a combiner box. We don't need to bring 500 volts DC down from the roof. We're going to convert at the roof, and with the IQ7, one per panel, and they are natively maximum power point tracking. And so if we shade one panel, we don't care. The other panels will continue to put out. And what we're dealing with coming off the roof is 240 volts AC right into our loads panel. What's the other advantage here? This is the basic solar system most people buy, and for economic reasons. They will have a series of panels on the roof, the microinverters, one with each panel, or one for every two panels, and then 240 volts AC down into their loads panel. Now, the way this is supposed to work is that your grid input, the microinverters have to have that to produce a waveform and an output. They simply shut down without it. They have to have something to sync to. And this is an anti-islanding provision required by Underwriters Laboratory 1741, which the utilities are all about, because they don't want, in theory, they don't want your solar installation to power the grid when the grid's down, because it might injure a maintenance person. This is an absurd notion. No utility grid maintenance personnel has ever been inconvenienced in any way by a solar installation, but that's their sort of red herring excuse to be able to control your power. The problem is if you lose the grid, this doesn't put out any power, but it's quite inexpensive and simple. You simply have microinverters that then put 240 volts AC here. If they detect a grid waveform, 60 hertz, 240 volts AC, grid waveform, they will begin to produce power, and they'll produce it at a slightly higher voltage than the grid. And so they will provide the power for your home through the loads panel normally. And if they provide more power than your loads in your house, your vacuum cleaner, your air conditioner, your refrigerator, and your lights, because it's a slightly higher voltage it would feed right back into the grid and ostensibly run the meter backwards, for which you would be handsomely compensated by a generous and loving Ameren UE type utility company. We're eschewing the kumbaya moment, and we don't want to sell them anything. We don't want to give them anything, and we want as little as possible from them. But that's how the system normally works in 97% of the installations in the country. Now, this is an economic decision. A battery backup is expensive. It will take your solar installation to 1.5 times to 2 times your overall installation. In other words, if you're putting in a $30,000 solar installation, if you want battery backup, it'll be anywhere from $45,000 to $60,000. Well, that's to give you power during the 3 15-minute outages you encounter in a year. By the way, this number is changing. In 1980, there were 5 measured power outages in the United States in the course of a year. In 2016, there were 550. And so the utility grid is doing less well all the time at being reliable power. And of course, in many countries, you get power 2 hours in the afternoon if you're lucky. So we're trying to come up with a strategy to add battery storage to the 97% existing solar installations that don't have it, and they almost universally use grid-tied inverters that require a grid waveform to operate. In our case, we're going to provide that with our inverter output, which is 240 volts AC, 60 hertz. And our batteries are going to power that. But when they do, they will trigger these microinverters to come on and produce power. And during the day, they will most likely produce more power than we are using in our loads panel. And that power will feed back through this output transformer and these this H-bridge switching mechanism and right into the batteries. And everyone will tell you this won't work, including the manufacturer of this inverter has described for me in detail why this won't work. And I can measure it all day long, and it not only works, it's flawless. It works fantastically. Up to the point where the batteries get full, and I disconnect the battery to prevent overcharging the battery with the battery controller. At that point, all hell breaks loose. But the basic concept is the inverter, of course, shuts down because we've cut off the battery, and then the inverters shut down. And hopefully all that happens in an orderly fashion, but not necessarily. And so we've done some experiments with it. We shut it down successfully without damage to equipment. But we don't want to do that very much. And so we've added a component here, a contactor, that disconnects one leg of the grid-tied solar. And in doing so, now they've lost their waveform and they shut down voluntarily because they think they've lost the grid. And so we can do that when the battery gets full, run off the batteries for a while, providing our loads, and run that battery down a little bit, say to 3.9 volts per cell, and then we will cut it back on. And with a 5-minute delay, these will come up again and start producing power. And so that's an overall summary of our system for those of you, and our mission. Our mission here is to develop a selfish solar system that only uses the grid as the backup. Instead of becoming the main plant, it's now the backup, and the batteries, instead of being the backup, are now the main source of power. And they are replenished by the grid-tied solar panels, which produce power that go to our loads during the day, and in their excess, they feed it back into the batteries, bringing them up to full charge for the evening, at which point these go down anyway because of the lack of sunlight, and now we produce power overnight from our batteries to all of our loads to operate our house, or in our case our shop, overnight. And then the next morning, when the sun comes up, these will again begin producing power, and when they get to where they're producing more power than we're using, it will again recharge the batteries. 2 or 3 o'clock in the afternoon, they get up to full batteries. We disconnect it for a few minutes, 15, 20 minutes, run off the batteries, and then reconnect it to bring the batteries back up to top them off again, and then disconnect them for 15, 20 minutes. And we top off the day with this kind of slow cycle to top off, to keep the batteries in the topped off state without overcharging them. And so that's our 24-hour cycle. If we have sufficient solar panels, and if we have sufficient battery storage, then we are basically generating power at the point of use with minimal dependence on the grid for anything. And as I said, we can replace this grid with a generator in installations that don't even have a grid. But I would advocate paying the $11 a month to have a grid for 7 days of snowfall in December, when we're having not very much power from sunshine. So that's the concept and the mission. And before you rush out and install this on your roof, understand that this makes no economic sense at all. To avoid your 12 cents kilowatt hour grid thing, this is a preposterous level of expense, and cobbling together different equipment, salvaged EV batteries, a Chinese inverter, contactors, and so forth, to accomplish this. And it's not going to work out for you. You're not going to save money with this. It'll pay itself off in 140 years. That said, I actually think this is the model for the future, and that eventually this will be not only economically viable, but at a huge savings from the future grid, which, because of a combination of factors, is inevitably going to see a 5 to 7 multiple on what you pay for electricity in 10 years. And so this is a experimental situation. It is, for many of our viewers, pay to play, to be the tinkerers and the innovators, leading the way into the future. And for their own edification and education, they play with this to get to be one of the first that sees the future, not that profits by it. Generally speaking, if you see Jack Rickard playing with it, you can't afford it, because it doesn't make any economic sense. But in the future, it'll be exactly how it's done. And I think this will be the model. Grid-tied microinverters. Actually, I think the model will be a roof that makes power synced to a central battery-driven inverter, and that is used to charge the batteries, and then the batteries discharge when there's no sunlight. We don't have or need any of this, and the microinverter is built into the panel, and eventually the panel is built into the roof. You have to have a roof anyway to keep off the rain and the sun. Eventually we want it to produce electricity, and traditionally, and for a variety of reasons, the standard is 240 volts AC. And so that's what your roof will produce. That's what we want to produce from the batteries, and it's important we be able to get that energy back into the battery. This is going to be the model for the future. and the day will come, and it won't be too far off. I usually like to peer about 12 to 15 years out, and so if I'm playing with it, it's something you're going to see, and you're going to start seeing quite a bit of in 10 years, 8 or 10 years, and in about 15 or 16 years, it will take off and become mainstream. So that's kind of the timeline you're on, and let me again reassure you that none of this is, you can't get a 4-function calculator to work on this now. The only reason you would want to play along with me is for your own education, and to perhaps learn techniques that are simply not known now. And I can assure you the idea of AC coupling directly into batteries backwards through the inverter is not just unpopular, but 99 out of 100 solar professionals will tell you it's not even possible. Almost all the inverter manufacturers will assure you that it's an absurd notion, and we're doing it day and night. Okay, just a quick word on motivations. I've kind of glossed over that. Why does the grid want to protect their maintenance workers from solar panels, and have insisted on this UL 1741 anti-islanding provision to protect their workers? This is nonsense. There's never been a grid maintenance worker injured ever in the history of the world by a solar installation. In my home in Denver, in 1998, I installed the full grid-tied system, but it had a automatic transfer switch on the input that if you lost the grid, it disconnected, and you had to manually reconnect it once the grid was back up to go back on grid. So there are no safety provisions necessary. The utility companies have insisted on UL 1741 compliance, an anti-islanding thing that has to be built into these microinverters. Any grid-tied inverter has to be UL 1741 compliant, and their story is to prevent injury to a worker. That's not their motivation in any sense, and never was, even for a moment. They actually want, when you lose grid power, for you to also use solar power. Now, why would that be? Well, in the event that the grid goes down, if your house continues to operate off of solar power, that's going to kind of plant the seed in your mind that why do I need the grid in the first place? This is a control issue. They want a legal requirement for your system to be disabled when you lose the grid, so you'll be dependent on the grid. If you're not dependent on the grid, they fear that the Indians will start to wander off the reservation and look for ways to expand the solar system such that they don't need to be a customer of the utility anymore. This is very self-serving, it's very obvious, and they are being deliberately deceitful, as in lying, with this whole concept of harming maintenance workers with your solar system. It's something that appears to make sense on the surface, but it's kind of like all the blind people being run over by electric vehicles. They passed laws to require you to make noise so we can end the slaughter of innocent blind people who are being run over by silent electric vehicles. There's just one problem with the theory. There's no case of it ever happening, ever anywhere. And this is the case with the ostensible excuse of the grid-tied inverters. Now, we actually have a fairly impressive number and a growing number of people who are going to the expense that I've just described to you. Makes no sense at all to do this thing. Well, this is I'm being a little disingenuous here. It's a little uncomfortable to talk about, but a large portion of the incidence of building electric vehicles and buying and driving electric vehicles is not so much to be green and save the planet as it was a deep desire among a certain element of our viewership who had felt manipulated and cheated by the oil companies to tell the oil companies to fuck off and die. And right now there are numerous instances of these arrogant, abusive utility companies mauling their customers, and their attitude is, hey, there's nothing you can do about it. You gotta have us. We're a monopoly, and so we don't have to respond to you at all. And a couple of those incidents can cause deep anger, a deep sense of injustice, and we're right back where we were with the EVs. A lot of our viewers simply want to tell the utility companies to fuck off and die, and they don't care if it's $10,000, $100,000. Some of them will spend $1 million to do this. And then you have beyond the FOAD crowd, there is a legitimate need, and I hear from people all the time in Puerto Rico and Costa Rica, the Philippine Islands, where they simply don't have reliable grid power. They might get it 2 hours a day, and they want to lead a modern life and have modern appliances and air conditioning, and so they're looking for ways to develop their own power. And so that's a very real and legitimate need. It's not about how much the power costs. It's that they can't get it at any price. And they're looking for the simplest and the easiest and the least expensive way to produce their own power plant. And so that's kind of what this is about. But a lot of our viewers are, yeah, they want to tinker and innovate and be part of the future, and maybe develop a device or a technique or that can lead to a little business or a big business, and to be a player in the future solar economy. But to a larger extent, it's more of a fuck off and die situation, and they'll spend kind of whatever they have to do that. And so this, if you're a happy utility customer paying 12 cents a minute for electricity, none of this is going to apply to you for 15 years. Eventually it will, and eventually you'll be very unhappy, because as the adoption of incandescent, the translation from incandescent light bulbs to LED light bulbs occurs, there's going to be a 20% reduction in the requirement for electricity across the country. And they're simply going to make that up by increasing the rates. That's going to increase the adoption of solar plant in businesses and residences, and that's going to drive up the cost further. And so we're going to be in a upward spiral of utility rates. They don't lose money. They're the stock of choice, paying dividends into retirement plans, and the legislatures simply rubber stamp their rate requests in most cases, and if they actually have increased costs in all cases. And so you're going to see, I think, a 4 or 5x increase in utility rates over the next 10 years nationwide here in the U.S. And it's because of declining revenues from a ever-shrinking customer base as people adopt more energy efficient applications, I think you'll see as the rates go up, the air conditioning systems become more efficient, more geothermal, more LED lights, and it's kind of a spiral. The higher the rates go, the more will be spent on reducing power usage. And you have, going with that, the movement to producing your own electricity at the point of use. And this will spiral out of control at some point. So I'm kind of readying you for a future that's, in my mind, already happening. And so I'm almost predicting the history rather than the future. And that's how it generally feels. But I wanted to mention some of the motivation here, both on the utility side and the strange things you see our viewers doing in spending money on systems that you can't do the normal payback period concept, and sort of their view is, my view is, what's the payback period on your 65-inch flat screen TV, or what's the payback period on your couch? Don't get me started on the price per pound for bass fish meat here in the U.S. And so it is a discretionary expenditure done for education and demonstration, and a vote or a stroke toward independence from the large corporate structures that have become so abusive to their own customer base. So we're going to take a look today at operation of our system with the ENphase IQ7 microinverter. That's the most recent grid-tied microinverter from ENphase, and I think one of the best in the world. So let's set our life alerts to stun and cinch up your depends, old guys. We're going in. Okay, I'm here with Slumdog Millionaire and the PowerPhase 100, and we have our orange cable going through, and I've got some video I'll put up here, our solar shutoff, which we have a mechanical shutoff we can turn off and on, and a contactor that we can turn off and on. And then that goes into the next box and ties in with the output of our inverter. And I have that up right now. You can see on my little display, it says about 0.16 kilowatts. It's actually 145 watts on the ASCII text thing that we are discharging. That means, and we're not hooked up to anything. And so we, it costs us about 145 watts not to power anything except the inverter. And what I'm going to do, we have charge enable on right now. I don't know why I had put it off. Let me try again. That's off. Yep. Oh, and it keeps coming back on. Oh, I know what I'll have to do. Change my resume to a lower value so I can manually do this. And let's say resume equals 3.00. Now let's go back over here, and we're all up at 3.3 and so forth. So I can set my charge enable to off, and what that does is cut off my with the charge enable off, we're not connected to the ENphase IQ7. Actually, just one leg is opened up, and we're sitting here discharging at 3.54 amps, which we're reading as 4 amps over here on the display, at 145 watts discharge, just to have the inverter lit.
and be running our BMS and so forth. And so we're using some power there. I have my little phone going here with its stopwatch. And what we're going to do is set charge enable on manually. And that's going to close that contactor. And I'm going to start our clock. And right after 5 minutes, with a little bit of luck, we're going to get some power from the ENphase. What is our voltage, Danu, on our output of our inverter right now?
244 volts AC.
244.1. 0.1. And I'm going to write that down. And you'll see something interesting here, that the inverter is making 244.1, but we're going to measure that again when the ENphase IQ7x's come up. And I'm predicting that that's going to be about 5 minutes, maybe a little over, because that's what the Solar Edge takes to do that. And so basically we're sitting here, we're not connected to power anything in the shop. Our output is completely disconnected from the world. We don't have any charging input. We're running off the batteries and making about 145 watts just to stay alive. And we have our charge enable on, so our contactors close, and we're putting 244.1 volts to the ENphase IQ7x's that are out in the parking lot. Now it's after 5 o'clock, so we're not going to get much, but we should be able to measure. You should be able to see here. Right now we're having very slight red here, and on our power log, we're just a very small discharge, which it's reading as 160 watts. Okay, we're at 4 minutes and 18 seconds. I'm still showing a discharge of 3.55 amps, right at 145 watts on our PowerPhase100 inverter. And we have our charge enable on, and it has been on for 4 minutes and 40 seconds. And we're going to monitor that as we come up on 5 minutes. And what we're looking for is a change from a very slight discharge of 145 watts to some form of charging. And there's 5 minutes and no joy. We're still discharging. And there's 5:10, and it's not getting any better. Oops.
Yep.
Suddenly at about 5:12, 5 minutes and 12 seconds, we are now charging at 8.3 amps and 339 watts. 339 and 145 is 479, 483 watts of power that the 325 watt panels are making, kind of nearly flat on the ground and at 5 p.m. But we have brought them up using the waveform. What's our voltage now, Danu?
245.9.
245.9. And what that is all grid-tied systems. Try to lock into phase and frequency with the grid voltage, and we're at 59.86 hertz on our power safe, and they bump the voltage just a little bit. They put out a little higher voltage than whatever the grid is doing, so that they act as the current source. And these have come up right at 5 minutes and 12 seconds, and we are indeed charging using our IQ7X. And so this test is very oddly a success in all respects, leaving us with no particular anomalies to investigate. And what a boring afternoon. We have been playing with a Solar Edge 5 kilowatt wall inverters, and the question has been, well, whether these little microinverters would work the same way. And I'm pleased to report that they not only work the same way, but uneventfully so. When we provide them with 244.1 volts, 5 minutes and 12 seconds later, they respond by outputting 244.9 volts and pumping, in this case, about, we're up to 360, about 500 watts of charge into our batteries, charging at 8.85 amps. And so we can scale that up to whatever you want. That's with 3 panels and 3 ENphase IQ7x microinverters. With 40 panels, we can be putting quite a bit of current into this battery. And so that's the thing. 40 panels would be about 12 kilowatts of power at 325 watts each. 12 to 15. Of course, you're never quite, that's the maximum output. Maybe 1 o'clock in the afternoon on June 22nd. But the point is that these work exactly identically and just as smoothly with the ENphase microinverters as they did with the Solar Edge. It also shows me, and we know that this would be so, but we never actually tested it, that by having a contactor in our solar input box that we can control with Charge Enable, we can charge those batteries right up to our cutoff voltage, at which point we disengage that contactor and that whole system goes down and will no longer produce power and will not overcharge our batteries. We can then make power out of the batteries at off the batteries make power until we get down to our resume voltage, which we'll set at 3.9 or something, and at which point it will close the contactor, and it takes 5 minutes and 12 seconds for the ENphase to come back up then and start charging again. And so you'll do that in the afternoon. You'll charge all morning till say 2 or 3 o'clock until you reach full on your batteries, and then it'll sit there and cycle on and off, but slowly on a 20 or 30 minute cycle, and do that until the sun goes down, and then it'll be ready to charge when the sun comes up in the morning, and you operate off the batteries at night. But you go into the evening with a mostly full pack, depending on where you set your cutoff and resume. And so this is going to work quite well. Our Charge Enable and our contactor can control it rather positively, and it works with both the Solar Edge inverter, which is probably the most popular residential grid-tied inverter out there, and the ENphase, which is probably the second most popular, and that's the microinverters, 1 per panel on the roof with 240 coming down. And so we continue our examination of charging our batteries using AC coupling from grid-tied inverters and eliminating the grid and using the PowerPhase100 off-grid inverter to replace it. And I can't tell you, it's going suspiciously well at this point. I get uneasy when everything is just working as predicted. I'm so much happier when shit's blowing up and I don't really know what's going on and so forth. But today, this has been a fairly expensive non-experiment that took Danu and James 5 minutes to set up and wire up, and another 5 minutes for us to bring up and see what it was going to do. So I'm very encouraged. Walter Crumbly in Costa Rica specifically wants to use Panasonic HIT panels and the ENphase IQ7x microinverter, and it appears that it'll work fabulously and with no issues. Stay with us. More EV TV to come.
This man right here is my great-grandfather. He's the first cat herder in our family.
Herding cats. Don't let anybody tell you it's easy.
Anybody can herd cattle. Holding together 10,000 half-wild short hairs, well, that's another thing altogether.
Being a cat herder is probably about the toughest thing I think I've ever done.
I got this one this morning, right here, and if you look at his face, it's just ripped to shreds, you know?
You see the movies, you hear the stories, I'm living a dream. Not everyone can do what we do.
I wouldn't do nothing else.
It ain't an easy job, but when you bring a herd into town and you ain't lost a one of them, ain't a feeling like it in the world.
I am here with our EVTV hack team, Slumdog Millionaire and Dr. James the Gross. The friend of mine's son stopped by. He's with the local newspaper, and he wants to have a festival on September 22nd with 8 bands and food trucks and all this stuff. He calls it the Shipwreck. And for you in Cape, it'll be on August 28th from 11 in the morning till 9 o'clock at night. And that's the Shipwreck Shipyard Festival. He wanted me to sponsor that with him, and we got some other companies here in town, Rhodes and Brewery and so forth, and so we all did. And now he wants us to do something he saw at a festival in Chicago, which was a USB charging station. This is where attendees to the rock and roll concert can charge their cell phones, as I understand it. I'm otherwise occupied. But we have a couple of young and enthusiastic interns from Southeast, and I had initially turned this over to them. Of course, I couldn't keep my mouth shut and stay out of it, but they're mostly doing it and doing a bang-up job. We're taking our Tesla pickup truck and putting solar on it. And on the top, we've added a kind of a rack that we're going to put LED lights and stuff on anyway, and put a Panasonic HIT 325 watt panel. And then we've got these little sides that fold up and fold down, and we put panels on those with some stanchions, just little poles, to angle them toward the sun. And we're going to build the thing to charge USB charging ports. How's it coming, guys?
Let's get in there. It's going. It's going good.
So the idea is to take the panels and charge our 12-volt battery from them, and take the 12-volt battery and invert that, believe it or not, to AC, so we can convert it back to 5-volt DC for these kind of things I found on Amazon that will let you charge 15 phones at the same time. And they have little short USB cables, but they're the kind of the high current USB ports that allow you to charge fairly quickly a tablet or an iPhone. And so the concept is we're going to go park this at the shipwreck, and then people can come up and charge their phone. And he assures me this will be good for me somehow. And I feel that everyone should have charged phones. I'm a little bereft at the concept of people walking around with run-out cell phones. Not normally so much that I would do anything about it, but anyway, Gary Russ, the younger, wants it, so I've known his dad for many years. I guess we're gonna spend a few $1,000s and do that. But it'll give these guys something interesting to do, and they're having a ball learning a lot.
It's fun.
James, what's our maximum charge voltage and current for these panels?
The voltage is 58.7, and then the current is 5.47.
So 5.47 amps and 54.
Is that what I said?
Is that what you said? Well, I don't know what you said. That's why I wanted you to know this. And Danu, we're going to convert that to 12 volts using what?
We're using the PowerFlex Max 80, the
Outback Power?
Outback PowerFlex Max 80.
Flex Max 80.
Yep.
And what does that indicate it'll do?
So 80 is for 80 amps, and it can handle up to 1,000 watts with 12 volts.
With 12 volts. And with three 325 watt panels, what's probably the maximum power we're going to get out of this?
We should get about 975 watts.
975 watts in your dreams, but that would be the maximum, and that's what we're designing to. And then, James, we have an inverter.
Yep, we got the pure sine wave inverter that does 1,500 watts.
Okay. Let's put the lid on there and
Yes, sir.
see if they can see. So we've got a couple boxes here. We put the Outback in the aluminum box back there, and that's wired into our 12 volt battery. Now we could easily, I can turn on the car keys, we can recharge the 12 volt battery from a 24 kilowatt high voltage pack. But we're kind of putting on the dog here. We're charging their cell phones with cellular. I mean with solar.
Solar.
And so we're making a big show of having 3 solar panels and a charge controller and so forth, and that technically is providing the power to charge their cell phones, and we'll have that available all day from 11 to 9 p.m. And I happen to know it'll even work past sundown because we're hooked up to the 12 volt battery in the car. So that's kind of the rundown. What's been your biggest problem with this, guys?
I'd say trying to get these mounted, trying to figure out the bolts and everything for that, and also the weight of the panel on the tailgate, making sure the post is strong enough to hold it.
Dan, fold that one up and show them what it looks like driving.
So panel just goes up like that.
So it's just going to stick straight up in the air going down the road. We'll put some sort of lame decal work over here to advertise the event, I guess. And so we'll pull up and immediately set up our panels, and it depends on which way we're facing, whether this will be the tall side or the low side. And yeah, set that back down on your stanchion. And so you just unfold that, stick your stick in the hole in the end of it that's already there, and that's pretty sturdy. I wouldn't sit on it, but and that will gather photons, convert them to electrons, and stuff them into your smartphone. How cool is that?
Yep, that's basically the
Free
idea.
Coke for the kids. We kind of need something to give away or something to charge them.
Yeah.
Just some sort of transaction to do this. I don't know. I'm running out of ideas. It's just a big rolling cell phone charger.
Yep.
Yep.
What do you guys think of the project?
Me personally, I love it. I haven't really had too much work with solar panels, so being able to put them up there and connect the wires and do all that, it's just kind of something I've always wanted to do.
So you can be the main guy sitting with the truck all day from 11 to 9.
Yeah.
Danu, what's your position on the yellow Bumblebee cell phone truck?
Yeah, getting to work with the solar charge control is something I've actually never messed with that before. So understanding how that converts all the solar voltage into 12 volts that we can use is, I didn't think I would get a chance to play with that ever. So.
And I kind of went through an explanation of that. Why don't you give your understanding of maximum power point tracking to our listening audience? And by the way, we've got because of our venture into solar, we have I was looking at our tracking this morning. We've got a huge influx of people from India, which Danu is not actually from India. He's from Sri Lanka, but it's kind of over the same part of the world.
For the most part.
So, yeah, we're having a huge jump in viewership. India and the United Arab Emirates are probably China's getting into it too. The U.S. is the only lame country in the world about solar. The rest of them are kind of getting with it. India is installing some huge, I mean enormous, 600, 700, 800 megawatt solar installations. They're just enormous. And so what's your understanding of maximum power point tracking?
So if I remember right, I think it's, so when there's no load or when there's zero resistance, we have about 72 volts coming from these panels. And then when there is max load, so we have 0 volts coming from these panels. So what we do is, what the software does is, it finds that exact max point where the curves meet to get the maximum power, and it continuously looks for that max point each cycle. By sampling. By sampling. Yep.
Yes, that's essentially correct. If we have our max open circuit voltage, we don't have any current. Power is voltage times current, so we have 0 watts. If we have the two output connections shorted, we have maximum current but 0 voltage again, and so again we're at 0 watts. That'll make a curve as the voltage comes down and the current comes up. The power increases to a point, and then it starts to decrease. And so we can optimize the power output of the panels by simply modulating our load to that maximum power point. And it does this by simply sampling changes in current with changes in voltage. And it does that by varying the switching frequency of basically a switching power supply, which is what an Mppt charge controller is. And that seeks that point as the sun varies and as the load varies, it mediates that to get the maximum. In theory, you get about a 15% bump in what you harvest from the panels using that technique. You will see two types of charge controllers, PWMs and Mppt, and the only difference is they're both PWMs. The Mppt actually samples and seeks the maximum point where they get the maximum current times the maximum voltage, and locks onto that, and then a few seconds later it'll do the scan again. And so that's the difference. In large installations and at large currents, it doesn't matter a whole lot. But the smaller your system, the more likely you can take advantage of that 15% becomes a considerable issue. And Outback Power, probably most people's choice for the best Mppt charge controller. This one, little 80 amp thing, that's still pretty close to $500. But that's the one I picked, and I wanted these guys to get the fool with configuring it, and we've been playing this afternoon with how to get it to work with lithium batteries and discussing the vagaries of bulk charging and absorption and equalization, and why that is so out of bounds and a mess with lithium batteries, and how to trick this thing into doing the the right output for our lithium battery. So that is our solar powered solar electric cell phone truck, which I agree is kind of frivolous, but it suits my sense of whimsy, and apparently in this case pleases some sons of friends of mine for their shipwreck project to bring rock and roll to Cape Girardeau. And so it's given these guys a good project they can work on without my constant supervision and intervention. In fact, they're coming to me, but wanting to ask questions and stuff. I'm trying to stay out of it. And they've done very well with it. I think it's going to be beautiful and very effective at charging cell phones, if that's your mission.
Yeah.
We intend to eliminate discharged cell phones starting in Cape Girardeau, but we may take it on the road and go worldwide.
Worldwide.
Everywhere. Stay with us.